if I call, let's say these two figures, just the way I've set them up, they are similar. If they're similar, and I call, this side here A times H, and I call this side here C times H, what would the scale factor between these two figures be? From the blue one to the red one. What would it be? These two are similar. That's an A times H. That's a C times H. If they are similar, doesn't it mean that their sides are proportional? Meaning that AH divided by CH should produce my scale factor. What happens there? If AH divided by CH. Algebraically, what happens with the H's? They cancel out, and you're left with just A compared to C, right? We've talked about that is the scale factor for these side lengths, okay? Same idea. If I say this is A times B, and this is C times B, okay? What's going to happen when I compare those? Yeah, it's going to be A over B compared to C over B, which reduces to A over C. That's the scale factor. And what's going on here, maybe you wouldn't write it this way normally, but let's say this height here is 3. Let's say that A is 2. Let's say this base here is 5. And again, the A has to be 2. Over here, let's say that the H is 3, but now the C is 5. And over here, B would still have to be 5, but C is also 5. If I start comparing those 2 times 3 compared to 5 times 3, what's going to happen? 2/5, right? Or if I compare 2 times 5 to 5 times 5, still gives me 2/5. Or if I compare as this side being 6 and this being 15 and this being 10 and this being 25, is 6 to 15 going to reduce to 2/5? Is 10 to 25 going to reduce to 2/5? Okay. So when we talk about two shapes being similar, that's the idea that's happening. Okay. It might initially be easier for some of us to think about, why put that A on this smaller figure? Let's say A was 1. Then I have H compared to CH. And I have B compared to CB. Does that still give me 1 over C in both those? Does that make sense? Okay. But in general, we know that this might not always be a 1 out in front. So we put that A there. Okay. Or I'm going to put that A there. And now I want to go through, so that's the scale factor. These are linear relationships, okay? Which means it's one-dimensional, okay? If I find the area of this figure using this set of components, can I say that area of the blue figure, area of the blue triangle, is 1/2 the altitude, which we are labeling the altitude as AH, times the base, which we're saying is AB in this case. Does that make sense to everybody? So what does that give me? It gives me 1/2 A squared BH for the area of that blue figure. Is everybody okay with that? Okay. I'm going to find the area of the red figure. Area of the red figure is going to be 1/2. Now my altitude is CH, and my base is CB. Okay? So it gives me 1/2 C squared BH. Okay, 1/2 c squared BH, and that's the area of the reg. But when I compared these sides, compared that side to that side, okay, it gave me a linear relationship. I should be able to compare that area to that area and see what happens, okay? So when I do that, when I compare the blue one, which is 1/2 a squared BH, to the red one, which is 1/2 c squared BH, what happens with the 1/2s? Cancel out. What happens with the BHs? Cancel out. What are you left with? A squared over c squared. And that's the relationship. That is an area relationship. Okay, which is a two-dimensional concept, right? Okay. How does that relate to the side length relationship? How does it relate to AC? It's just the square of AC, isn't it? Okay. So what happens here, guys, is if I know the side lengths, okay, if I know how the side lengths relate to one another, so let's do a little bit of work here with GeoGebra's tools and see if we can make this argument. So similarity or scale factor, similarity ratio or scale factor was, what do we say, is A over C, okay? The area ratio was A squared over C squared. If I look at, let's see here, that distance right there being 10, okay? And now I look at that distance right there being 30. And even if I look at that one and that one, okay, is there a 1 to 3 relationship between that to that? So my scale factor here is 1 to 3, right? Is that the same 1 to 3 when I look at 20 compared to 60? Yeah, okay. That means then that whatever the area of this one is, okay, I should be able to determine the area of this one. All right. Now, this is the way I would do that. The area ratio is not 1 to 3. It's, this A is 1, right? C is 3. So A squared would be 1. C squared would be 9. So what's the area of this thing right here? Area is equal to 1/2 10 times 20, right? 10 times 20 is 200. Half of 200, 100. Okay. What is the area of this one? Yeah, 1/2 30 times 60, right? Okay, 30 times 60 is 1,800. Half of that is 900. What's the scale? What's the ratio of area to area? 1 to 9. Does that make sense? Okay. So where is that beneficial? Why is that beneficial? Because now if I know that these two things are similar, I don't need to find both areas because that might be time consuming. If I know they're in a ratio of 1 to 9 and this one's 100, don't I automatically know this one's 900? Okay. Or if I know that this one's 900, I should automatically know that this one's 100. Okay. So that kind of introduces us, and we could do that with any figure, any set of similar figures. It doesn't have to just be triangles. Every area formula we've talked about generates from base times height, right? So if we could do this, or base times altitude, we should do this for a parallelogram or a rectangle, and all our other figures are based off of that concept, then this is a true concept no matter what formulas we start with, okay? Whether it be 1/2 BH or 1/2 D1, D2, or something like that, it does not matter. So here's the argument that we're looking to make. Maybe. All right. The similarity ratio between two figures, if it's A over B, and the ratio of the perimeters is A over B as well. We've talked about that. I'll show you again here in a moment, maybe the algebra behind that. But the ratio of the areas is always A squared over B squared. Okay? So if you know the scale factor allows you to say how two figures are similar, you should be able to use that scale factor squared to tell you how the areas relate to one another. Okay. Occasionally you might see, because these are equivalent based off our laws of exponents, you might see this every once in a while written that way. Okay. Let's talk about the ratio of the perimeters. Why is that A over B? If I have, let's deal with two rectangles that are similar. Let's say we got this rectangle here and that rectangle there. And let's say that this rectangle is some A times W. Okay? And this here is A times L. Okay? So some length and some width. Okay? This here is some C times W, and this is some C times L. Both rectangles. Okay. Would you guys agree that these are similar by a scale factor of A over C? Okay. If I tell you that they're similar, so we know that, and then I go through and find the scale factor, AW, you guys agree at that? AW should compare to CW? And that's going to reduce to A over C, right? Can I look at AL, compare that to CL, and is that still going to reduce to A over C? All right, so we see the scale factor here is A over C. If I look at the ratios of the perimeters, okay, if we're talking about perimeters, what would this length right here be? Be AW, right? What would this length here be? AL. That's an L. For the same logic, this would be CW, and this would be CL, right? Okay, so let's do the perimeter of the small figure. Perimeter of the small one would be 2 AWs plus 2 ALs, right? That turns out, what do both these terms have in common? What does that and that have in common? 2A. If I take a 2A out, I'm left with W plus L. If I look at the perimeter of the large figure, it'd be 2 CWs plus 2 CLs, right? What do these two terms have in common? 2C, right? Take out 2C and you're left with W plus L. Okay? If I compare the perimeters through division, what happens with the 2's right here? Cancel out, don't they? What happens with the W plus L's? Cancel out, don't they? What are you only left with? A over C. Same thing as the ratio of two individual side lengths, corresponding side lengths, scale factor. Okay? So that's kind of the logic on rectangles. Now you go through the same thing with squares, you go through the same thing with triangles, all that kind of stuff. So whatever the similarity ratio is, and I'm saying similarity ratio, but that's another kind of synonym for scale factor. It is the same as the ratio of the perimeters. And then if I square that ratio, that is the ratio of areas. Okay? So I'm going to use that relationship here to kind of help us go through some practice questions. Should not be too difficult here. It says find the similar. These are two figures that are similar. Okay, they're telling us that they are similar. Ask us to find the similarity ratio. What would you argue that the similarity ratio is between these two figures, or scale factor between those two figures? Okay, 9 over 6, which reduces to what? 3 over 2. Okay, remember we always want the simplified one. Okay, so 3/2 is that similarity ratio. Okay, what is the ratio of the perimeters? still 3 over 2. Okay? Which is odd that we're able to know the comparison of the perimeters and not have a clue to what either one of these shapes' perimeter is itself, right? Okay? But this fact is true. If I know the ratio of one figure to the next, the scale factor, then the ratio of the perimeters is identical. I have no abilities right now to find the area of that figure or that figure, but I do know that if A over B is the scale factor, that leads to A squared over B squared being the ratio of the areas. So what would my A squared end up being? 9, right? Okay, take that numerator, that's A, square it, you get 9. Take my denominator of 2, square that, and I get 4. Okay, so that is the ratio of the areas between these two things. If I knew some more lengths, okay, and I was able to calculate the area of this and calculate the area of that, we would find out that they compare in this ratio to one another. Okay, what that means to me is that, let's say that this is a trapezoid that I'm trying to paint. Okay, if I painted 9 of those, okay, it would be the exact same area if I painted how many of those? 4 of those. Okay, or if I look at this one here and multiply that area by what ends up being, what is that, 2.25, okay, 9/4. If I multiply that area by 2.25, it should equate to that area. Okay. All right, so let's do another example. It says 2 similar polygons have corresponding sides in the ratio of 5 to 7. You don't know how many sides. You don't know if it's a triangle, if they're rectangles, if they're pentagons, octagons, whatever. You don't even know if they're regular or not. They're just similar. So you know all the side lengths correspond to one another and are proportional, and all the angles that correspond are congruent. Okay? What's the ratio of the perimeters if their scale factor is 5 to 7? It's 5 to 7. Okay? Don't know anything about how many sides I have, so I have no clue how to find a perimeter, but I do know that they relate 5 to 7. What's the ratio of their areas? 25 over 49. Okay? Not sure what formula is going to generate that, because I don't know if it's a square, rectangle, whatever, rhombus, hexagon, but I do know that their ratio is going to be 25 to 49 as an area. Okay? Does not say that one area is 25 square units. And it does not say that one area is 49 square units. Does that make sense? It means that they're in a 25 to 49 relationship. All right, so how is this useful? Okay, it's useful in being able to generate what an area of a particular shape is, knowing the area of another similar shape. Okay, so it says the similarity ratio of 2 triangles is 3 to 2. Okay, now when I look at that, it says the similarity ratio. That's another way of saying scale factor, right? So the scale factor is 3 over 2. And the scale factor is an A over B relationship. That's a linear or one-dimensional relationship. Okay? It says the area of the larger figure is 36 centimeters squared. That is a two-dimensional relationship, right? Or two-dimensional concept. So when I want to find the area of the smaller triangle, guys, when that's my goal here, which is a two-dimensional relationship again, or two-dimensional concept, I cannot use a one-dimensional relationship to do that. Okay? So if I want to find the area of the smaller figure, I cannot use that scale factor. Does that make sense to everybody? That scale factor is only going to find me linear dimensions. Okay? Meaning like just a left to right, or just an up and down, or just a forward backward distance. Okay? I'm trying to find an area. So if I have A over B as 3/2, what's A squared over B squared going to look like? 9 over 4, right? Okay. That is the area relationship between the larger figure and the smaller figure. That's how their areas relate. Okay. So now if I know that they relate in a 9:4 relationship, and I know that the larger one is 36 centimeters squared, do I have the ability of finding the smaller one? Yeah. Okay. Now when I cross multiply, and hopefully this is something that you guys recognize, I know that 4 times 36 is going to be 144. But I look at 9x equals 144, and I'm not maybe 100% sure on how to do that mental math real quick. But I do know this. I can write this as 9x equals 36 times 4, can't I? If I divide both sides by 9, it would look something like this. Does that mean I could take 36 over 9 and multiply that by 4? What's 36 divided by 9? 4. So it gives me 4. I have times 4. X gives me 16. Okay? That might be an easier way to do some mental math. Instead of saying 9x equals 144, and then grabbing my calculator and saying, oh, how many times does that work? Okay, how many times does 9 go into 144? So x is 16. Does that make sense? Well, if x is 16, okay, that is my a squared over b squared, right? We should always be able to check these things. That's my a squared over b squared. So what would a over b look like? 6 over 4, correct? 6 over a over b is a scale factor. It's a similarity ratio, so it should always be in lowest terms, correct? Is that reduced to 3/2? Yeah. Okay. So we're able to take our two areas and compare them, take their square roots, and get back to the a over b relationship that we know we should have had at the beginning or at the onset. So the area of that figure is going to be 16 square units, that triangle. All right. Do another example here. Two regular pentagons, and this is something to think about. No matter what two shapes you have, if they're both regular, they're always similar. Because regular meant same sides, or all side lengths are the same, meant equilateral, and meant equiangular, right? Well, if these two things are equilateral and equiangular, so these are all 10, 10, 10, and 10, and that's 4, 4, 4, and 4. Would you say that I always get a 10:4 relationship when I compare sides? Okay. We also know that that individual angle is n minus 2 times 180 divided by n. Okay. So if I do that, I get, what, 540 divided by 5 gives me that angle to be 108 degrees. If it's regular, they're all 108 degrees. Okay. Are these going to be the same thing? 108, 108, 108. Does that make sense, everybody? Still n minus 2 times 180 over n. So any two, so if I did that with hexagons or pentagons or octagons or decagons, if it's 2 decagons, 2 octagons, 2 pentagons, and they're regular, they're always similar. Does that make sense? It's a fact that we need to know. So here you're seeing that the scale factor, A over B, would be what? My only options are either 10 over 4 or 4 over 10, right? And because I don't tell you on order to compare them, it doesn't matter, which would be 5 over 2. Does that make sense? Now, A squared over B squared is going to be what? 25 over 4. Okay. Now, if I'm trying to use this information, trying to use these two things, A over B and A squared over B squared, to find an unknown area, which one of these do I use? This is a one-dimensional thing, and this is a two-dimensional thing. And we use this one, right? Okay. So the areas compare in a 25:4 relationship. Okay. I know one of those areas. So where should that go? Should that go up top or on the bottom? Huh? Why the bottom? Because it's the smaller one. Okay. So I put 27 0.53 there. And now, can I cross multiply? 4x is equal to 25. Now you grab your calculator for this. I got a GeoGebra here in a moment. I'll show you. But multiply those two things together, divide by 4, and you get something like 172.048 or something like that. Okay, I think it's actually like 0.675 with the rounding that we did. But this is the exact same picture. I guess I'm sorry, maybe you don't. You get that number, don't you? Is that the same thing? All right. So if I look at these, would you agree that that is 4 and that is 10? And then we'll look at that scale factor. That's a 2 to 5 ratio, right? Okay. This GeoGebra is developing our areas for us. Okay. So if I take poly 1, which is this 27.528 number, and divide it by poly 2, which is the 172.048 number, let's see what that gives me. It gives me 0.16. Well, I just compared that area to that area, right? So shouldn't that be the same thing as 2 divided by 5 raised to the second power, which is 4 divided by 25, okay? If I take 4 divided by 25, do I get the same 0.16? Okay. So those relationships are always going to exist, no matter what the area of this is. This is a 2 to 5 relationship with the sides, and it's a 4 to 25 relationship with the areas. Okay. Now, why is that beneficial? You guys remember the process for finding the areas of these things? 1/2 AP. Was that kind of messy and just a pain in the butt sometimes? What if I were to give you a question? That did something to the effect of this. Well, I just want to see that. I want to see them both shaded in. So if I shade that one blue, and I ask you, what is the area of just the things that are left red? You would have to find both areas and subtract them, right? And we have to do 1/2 AP for both from our previous concept. Okay. But if I'm going to find the area of those things using 1/2 AP, I know side lengths of both of them, don't I? Okay. So wouldn't it be easier just to find the area of maybe the blue one, and then compare side length of the blue one to the red one, and then determine what the scale factor is for their areas, and then I can determine the area of the red one or the blue one based off the other one. And that would be, it's an efficiency thing. It helps us get the area of both figures very quickly by just knowing the area of one of them. Does that kind of make sense? Okay. So there is a benefit to it. If you were ever to like go to the paint store and look on the back of a paint can, it tells you that X amount of gallons of this paint or quarts or pints or whatever will cover this many square feet. The way they get that information is using these types of scale factors. Okay. If you've ever bought like grass seed or something to spread on your yard, like weed killer, fertilizer, that kind of stuff. On the back, it tells you certain settings to set your spreader on and how many square footage that volume of whatever is going to cover. We use these relationships with area, linear dimensions, and eventually volumes to kind of predict those things. They didn't sit somewhere and say, if I put 1 gallon of liquid in, how much ground does that cover? And then do, okay, now 1.5 gallons, how much does that cover? Now do 2 gallons, how much does that cover? They might do like 10 gallons, see how much area that covers, and then realize, okay, we can start using ratios to say, well, if we don't do 10 gallons, if we do 3 gallons, how much is that going to cover? Does that make sense? So every time you see something on the back of a label of how much square footage something's going to cover, or how much volume something is going to incorporate, It's because of these types of ratios that they've able to determine that stuff. And that might be modeled maybe best in maybe an example kind of like this. Now I've got the answer here, so I want to kind of delete some of this stuff so we can work through it. All right, it says Benita plants the same crop in 2 rectangular fields. Okay. It says each dimension of the larger field is 3.5 times the dimension of the smaller field. Okay. And if you think about that, you don't really need to know anything about the larger field or the smaller field to determine this, but I think maybe drawing a picture here might be beneficial in showing you why you don't need to know that information. If I know that the 2 fields are similar, now this is not drawn to scale, but I don't know the smaller field, right? So let's just call this L and call that W, okay? Then this would be 3.5 L, and this would be 3.5 W, right? Okay. If I look at if they're similar, if I look at the scale factors, this is a 1 to 3.5, and this is a 1 to 3.5, right? Okay. If I look at the areas here, this would be LW, and this would be 3.5 squared LW, right? If I compare those 2 things through division, what happens to my LWs? They disappear, right? And I'm left with 3.5 squared to 1. Does that make sense, everybody? Well, how does that relate? Well, my scale factor is 1. I'll write this way, 1 to 3.5. That's the scale factor. That's a linear dimension. That compared to that, or that compared to that. Therefore, the areas are that number squared compared to that number squared. That's how the area should compare to one another. So that is 1 to 12.25. Does that make sense? Okay. So that's an A squared over B squared relationship right now. If I'm interested in knowing how much it's going to cost to seed the larger field, which one of these areas is representative of the larger field? The bottom one. So that's the dollar amount that is unknown right now. What's the dollar amount that it costs to seed the larger field? $8. Can I use that to say X is equal to $8 times $12.25? Or sorry, 12.25. That's just a ratio, so it doesn't have units on it. And that gives me then $98 when I multiply that out. Okay. Does that make sense? So you can use this type of stuff to kind of develop expected costs, develop expected kind of usages, like in regards to how much seed am I going to need to buy, how much fertilizer maybe I would need to buy, and that kind of stuff. Okay. Huh? Well, you don't know how big the field was. Is the field, is it in units of feet, or is it in units of meters or acres or something like that? And maybe it won't be a lot of money. I want to do one question from your homework with you, which is 10.4. I think it's question 10 out of your homework. And I'll just get you started on it because it's one that, in the past years, people have struggled a lot with it. Whoa. All right, so it's going to give you a picture like this, and I think it told me that the area of the smaller triangle was 108 square centimeters. Okay, it asks us to find the dimensions of x and y. Okay? Now, the dimensions x and y, this is a vertical distance, right? And up and down. This is solely a left and right. So when I find x, x is a one-dimensional distance or measurement. Okay? Y is one-dimensional. Area is two-dimensional, right? Okay? If I'm going to compare things, and looking at this, I know the area of this one. Do I know the area of this one? It's not explicit, but it is implied, isn't it? If it's a right triangle, you know you should be able to go 1/2 72 times 81, right? So that's, let's see here, 36 times 81 is 29/16. So there's the area of the larger one. So you now know an a squared over b squared. You know that 108 should compare to 29/16. Now I think just the way these are set up, that's going to reduce pretty nicely to 1/27. But that is a squared over b squared. Does that make sense? If I'm going to use that ratio, we use that ratio to help me find x and y, I cannot use it in that format. Because a squared over b squared is relating areas, right? To find x and y, I need to relate one-dimensional distances. So what does, if I look at x, what should x compare to? 72. So x should compare to 72. But those are linear dimensions, right? So what is the scale factor? If this is the scale factor for the areas, what's the scale factor for these distances? 1 over what? 1 over the square root of 27. And it's really the square root of 1 over the square root of 27, but square root of 1 is just 1, right? Because that argument here is if I'm going to use a ratio, a proportion to solve an unknown distance, I need to know what the scale factor of those things are. So take the square root of that, will give me a over b, right? Square root of that gives me radical 1 over radical 27. Now, radical 27, that's 9 times 3, right? So it gives me 3 radical 3 here. Cross multiply. So it's going to be 72. Radical 1 is just 1. So now I'm going to take x, and it'll be 72 divided by 3 radical 3. What do I need to do there? Simplify, rationalize by multiplying by radical 3 over radical 3, right? So 72 radical 3 over 9. What's 72 divided by 9? 8. So 8 radical 3 should be that value of x. You would then do a very similar thing with y, but you're going to say y over 81 is comparable to 1 over 3 radical 3. Cross multiply and solve for y.
Couldn't you also do 8 radical 3 over 72 equals 8?
Yeah, so if you wanted to go, so he's saying, could I do 8 radical 3 over 72 is equal to, would it be y over 81? That would be fine as well. Okay. My thought, though, is this 3 radical 3 is a smaller coefficient than that 8 radical 3. So your mental math might be easier with the 3 radical 3. But by all means, what you said is perfectly fine as well. So I'll open that up, 10.4. That'll be due tomorrow, and you guys may head to lunch. Thank you, you too.